We're used to explosions on Earth doing a lot of damage, but compared to the most energetic explosions that have ever occurred in the universe, they're pretty small potatoes. And it turns out those aren't even the biggest explosions because there's one more that dwarfs them all: gamma ray bursts. Let's take a look at what these cosmic death rays are, how they happen, and what they could mean for life beyond our planet. Let's start off by talking about just how powerful gamma ray bursts are. First of all, they're called gamma ray bursts because they emit huge amounts of energy in the form of gamma rays. Gamma rays are part of the electromagnetic spectrum. They have very short wavelengths and very high energies, which means they can do some serious damage. But the amount of gamma rays emitted during a gamma ray burst is absurdly huge. The most powerful ones can release 10 trillion times the power of the sun in just a couple of seconds. Now that much power does a lot of damage, which is why if you were anywhere near a gamma ray burst when it went off, you'd be dead. How far away you need to be to survive depends on the exact details of the event, but you probably want to be at least a light year away, which is definitely something to keep in mind if you're planning on traveling through space anytime soon. As for what causes these bursts, it turns out that we actually know about two different things that can cause them: collapsing stars and neutron star mergers. In both cases, though, the basic idea is that you have a bunch of matter crammed together in a really small space. That matter exerts a lot of pressure outward, opposing gravity, trying to pull everything inward. When that pressure can no longer support itself against gravity, everything collapses. In a massive explosion, in the case of a neutron star merger, you have to separate neutron stars that get close enough together that their outer edges touch. At that point, gravity takes over and pulls the two neutron stars together until they merge into one. In either scenario, the collapse happens extremely quickly, in just a few milliseconds, although there can be an extended period before that where the star is unstable and oscillating with lots of energy being released in little pulses. Some of those pre-burst oscillations are so regular that astronomers have been able to use them to measure things like the strength of gravity around neutron stars. As for the actual burst, it happens when the core of the star, or the combined core of the two merging neutron stars, collapses in on itself. That sends a shock wave blasting outward through the star, kind of like dropping a pebble into a pond. But instead of ripples spreading out on the surface of the water, the ripples spread out in all directions through space-time itself, which is totally wild. The matter just outside the core bounces back a bit when it hits the shock wave, but it's moving so fast that it just blows right through the star's outer envelope, blasting it apart and releasing all the energy inside. The energy is released in a very short time frame, too. We're talking less than a second, which means that the photons produced don't have time to spread out much before the burst is over. So they all travel together in a big bright beam that blasts out from the collapsing star. And unlike most astronomical phenomena that tend to be fairly spherical, the beaming effect means that gamma ray bursts can be really long, narrow cones. Some are less than 1 degree wide, which is really narrow when you consider that the sun is about half a degree wide. Now, sometimes the beams are wide enough that they spread out into nearly all directions. When that happens, the burst looks like a giant fireworks. It might seem like the beam spreading out would make the explosion less intense, but it doesn't. It turns out that the total amount of energy emitted depends only on the energy in the initial shock wave. Since that's the same no matter what direction you shoot it in, the energy is spread out over a larger solid angle, which makes each individual photon less energetic. But that doesn't change the total amount of energy released in the burst. Now, this also means that while gamma ray bursts are among the most energetic explosions in the universe, they aren't necessarily the brightest. It is possible for a burst to blast out a huge amount of energy in a very narrow cone, in which case it's incredibly bright. But if it's blasting out photons in all directions, it'll be a lot dimmer. How bright a gamma ray burst is gives us another piece of information that helps astronomers figure out exactly what's going on with these events. For instance, scientists think the ones that come from neutron star mergers are generally brighter than the ones that come from collapsing stars, which makes sense because you start with more energy in the system when you have two neutron stars than when you have one. It turns out that gamma ray bursts are actually incredibly useful for probing a number of different things about the universe, like how matter behaves under extreme conditions and how stars die. And they've even helped us learn more about our own solar system. For instance, scientists think that a gamma ray burst could be responsible for the excess nitrogen and other volatiles found in Jupiter's atmosphere. These bursts could also play a role in helping life get started on planets. It might sound surprising given how deadly they are to life as we know it. But on rocky planets, the intense radiation can vaporize surface materials and carry them into the atmosphere. On Earth, this process is believed to have vaporized a lot of the planet's original rock and released gases like water vapor, carbon dioxide, and nitrogen into the atmosphere. Those gases then condensed and fell back down to the surface as rain, forming oceans and lakes. So depending on what else is going on the planet, including whether or not it's still volcanically active, a gamma ray burst could be the thing that kicks off life as we know it. Now, this isn't a new idea. People have been suggesting that gamma ray bursts could have triggered life on Earth before. But recent research suggests that they might be more common than we thought, meaning that they could be more important for life beyond our solar system. One study published in 2023 estimated that there are roughly 3 bursts happening within 10,000 light years of Earth every year. And while that seems like a lot, it turns out that gamma ray bursts are probably much more common than that. The problem is that they're so brief that it's really hard to catch one happening. So any estimate of how many are going off nearby is just that, an estimate. There are a few different ways that astronomers try to find gamma ray bursts as they're happening. One way is to use satellites like the Swift and Fermi satellites that are constantly looking for gamma rays coming from all over the sky. Another approach involves looking at the optical or visible light part of the spectrum. Astronomers often focus on this because it's easier to detect than gamma rays here on Earth. For instance, in 2023, astronomers detected what was probably a gamma ray burst by looking at a star that suddenly got a lot brighter in visible light. Then, once they checked the data from other telescopes, they saw a bump in gamma rays as well. And just last month, a team of astronomers reported detecting a gamma ray burst using the All-Sky Automated Survey for Supernovae, or ASASSN, which is focused on looking for supernovae. In this case, they saw a star in a distant galaxy rapidly brighten and fade over the course of a few days. Now, there are other ways to spot gamma ray bursts. For instance, gravitational wave interferometers like LIGO and Virgo can detect the gravitational waves produced by merging neutron stars. And if you know where those gravitational waves came from, you can go look at data from gamma ray detectors to see if there was a corresponding burst. That's how astronomers made one of the most precise measurements of the speed of light, yet using data from GW 170817, the first gravitational wave signal detected from merging neutron stars. These days, astronomers have gotten pretty good at spotting gamma ray bursts. They've identified more than 100 of them, although they haven't confirmed that every single one of those was a long, bright burst like we've been describing. Some of them might be X-ray flashes, which are similar but less energetic. Others might be soft gamma ray repeaters, which are even more similar but produce lower energy photons. While we continue to work out the details of exactly what's going on with gamma ray bursts, we can be pretty sure that they're always incredibly energetic and potentially dangerous. But they are also an amazing opportunity to learn more about the universe and maybe even reset life elsewhere. Thanks for watching this episode of SCI Show Space.